When your email inbox filters out a spam message, or a self-driving car swerves to avoid a shadow on the road, the technology feels intuitive, almost like it's thinking for itself. But there is no conscious mind behind the screen. What you're actually seeing is the result of a mathematical engine designed to recognize patterns. To make these systems work, engineers had to move away from the traditional ways we've been talking to computers for nearly a century. For decades, programming was a matter of strict if-then logic. A human programmer had to manually write out every single explicit instruction for the machine to follow. That works for simple calculations, but it hits a wall in the real world. Try writing an if-then rule to identify an apple in a photo. You would have to manually code for every possible geometric shape, lighting condition, and color variation. It's an impossible list of rules to write by hand. To solve this, developers inverted the model. Instead of feeding the computer rules to get an answer, they fed the computer thousands of answers and asked it to figure out the rules for itself. This shift, moving from strict human instruction to a system of self-derived experience, is the core of machine learning. Think how a toddler learns to recognize an apple. You don't give them a botanical definition. You hold up a red fruit and you say, apple. You show dozens of different examples until their brain subconsciously recognizes the patterns of the stem, the shape, and the color. Machine learning replicates this process in code. We start with raw data, the examples, and pair it with an algorithm, which is the specific mathematical strategy the computer uses to study those examples. During the training phase, the algorithm sifts through the data to recognize structural patterns. It fuses that knowledge into a finished trained brain called a model. Finally, we reach the testing phase. We present the model with a new piece of data, and it uses its learned patterns to output a prediction. This single cycle of providing examples and testing predictions can effectively replace millions of lines of explicit human-written code. There are three main ways we facilitate this training. The first is supervised learning. We act like a teacher with flashcards, giving the machine strictly labeled data, like medical scans tagged as malignant or benign, so it learns to classify new data based on clear right and wrong examples. Next is unsupervised learning. Here, the machine is given a massive pile of completely unlabeled data. It is forced to find hidden structures and similarities entirely on its own. Businesses rely on this method to segment complex customer purchasing behavior or to detect anomalies like fraudulent financial transactions. Finally, there's reinforcement learning. It's trial and error. A machine is placed in a digital environment and given rewards for correct actions and penalties for wrong ones. Eventually, it takes a perfectly balanced step forward, allowing it to master complex tasks. Regardless of the learning style, the machine develops its own internal logic for processing data, often finding correlations that aren't immediately visible to human observers. Beneath the metaphors of toddlers and classrooms, the learning process is high-speed, heavy mathematics. It relies entirely on linear algebra, multivariate calculus, and probability theory. While old supercomputers relied on brute force human programming to beat grandmasters at chess, modern machine learning processes millions of abstract variables instantly. This list shows 10 specific ways the Indian Railways network uses these systems. The underlying math now predicts equipment failures, manages asset tracking, and optimizes the logistics of one of the world's largest transportation systems. Machine learning has moved beyond being an experimental software tool to become the invisible, load-bearing infrastructure of the modern physical world. But this system has a vulnerability. As a pattern engine, it is mathematically dependent on the quality and volume of the examples it is fed. If the historical training data is flawed, incomplete, or biased, the machine won't correct it. It will mathematically amplify those human flaws directly into its predictions. Today, the human role in this process has completely shifted towards selecting and refining the curriculum that teaches the machine. The central tension of our future is not whether machines can learn, but how the data we provide them defines the decisions they make.